Welcome back to the channel. In the quiet darkness of the cosmos, there are places where the rules of reality break down. Places where time stretches and space bends, where light itself is trapped. These are black holes, cosmic monsters with the power to warp the very fabric of the universe. But how do they work? And how exactly do they twist time and space? Let's begin with gravity. To most of us, gravity is the force that keeps our feet on the ground. It's what holds the planets in orbit and shapes the motion of stars. But over a century ago, Albert Einstein changed everything with his theory of general relativity. Einstein didn't see gravity as a traditional force. He saw it as a consequence of something deeper, the curvature of space and time. According to him, mass doesn't just exist in space, it shapes it. Imagine space-time as a giant sheet. Place a heavy object on it, a bowling ball say, and the sheet curves around it. Smaller objects roll toward the depression, not because they're being pulled, but because they're following the curve. That's gravity. Not a force pulling objects together, but the geometry of the universe guiding them. Now, take that idea to the extreme, and you get a black hole. A black hole forms when a massive star runs out of fuel. It collapses under its own gravity, compressing all of its mass into an incredibly small point known as a singularity. This point is infinitely dense, and around it is a boundary called the event horizon, the point of no return. Cross that line, and not even light can escape. Not because the black hole is sucking things in, but because space-time itself is so curved, so warped, that all paths forward lead only inward. Here, the warping of time and space reaches its extreme. Let's start with time. Time, we often think, is constant. 1 second for me is 1 second for you. But near a black hole, that's no longer true. According to general relativity, time slows down in stronger gravitational fields. This is called gravitational time dilation. Near Earth, the effect is tiny, measurable only with precise instruments. But near a black hole, the difference becomes mind-bending. If you hovered just outside the event horizon, time for you would crawl. A minute near the black hole might be years, or even centuries, for someone far away. This isn't science fiction. It's a real prediction of Einstein's equations. And it's been confirmed by experiments, such as those comparing clocks on satellites with those on Earth. But in the extreme environment of a black hole, this becomes far more dramatic. If you could observe someone falling into a black hole, you'd see them slow down, frozen in time, never quite crossing the horizon. But from their point of view, they fall right through. This difference between outside observers and those near the black hole is not a glitch. It's reality. Time itself becomes relative. But it's not just time that's affected. Space bends too, so severely that normal geometry breaks down. In our everyday experience, space is flat. You walk in a straight line, and the shortest path between 2 points is, well, straight. But near a black hole, straight lines become curves. Even light follows these curves. If light passes near a black hole, its path bends. This effect, called gravitational lensing, can magnify and distort the images of distant galaxies. Black holes, in a sense, act like cosmic funhouse mirrors, stretching and warping the light of the universe. In fact, if you were to look directly at a black hole surrounded by glowing gas, you wouldn't just see a black disk. You'd see a halo, a glowing ring of light bent all the way around. So you see the back of the black hole's accretion disk as well. This isn't an artist's rendering, it's real. In 2019, the Event Horizon Telescope captured the first actual image of a black hole. A shadow surrounded by light, bent by gravity itself. It was a photograph of space-time being twisted. But the story goes deeper. Because inside the event horizon, the rules change. Space and time swap roles. Normally, you can move freely through space, but only forward through time. Inside a black hole, time becomes the direction you fall. You can't stop. You can't turn back. Just like you can't stop aging, you can't stop falling toward the singularity. It's not just that you're being pulled. It's that the structure of space-time demands you move inward. Just like we must move forward in time, anything inside a black hole must move toward its center. This breakdown of space and time isn't just bizarre, it's one of the biggest challenges in physics. Because at the singularity, where all this mass is concentrated, our laws of physics collapse. General relativity says one thing, quantum mechanics says another, and right now, we don't know how to reconcile the two. This is the frontier of modern science. But what if black holes aren't the end of the story? Some theories suggest they might connect to other universes. Others speculate that information entering a black hole isn't lost, but encoded on its surface, hinting at a deeper connection between gravity and quantum theory. Stephen Hawking famously proposed that black holes might slowly leak radiation, what we now call Hawking radiation, eventually evaporating over trillions of years. If true, it raises a troubling question. What happens to the information inside? Quantum mechanics says information can't be destroyed. But if black holes evaporate, where does it go? This is the information paradox, one of the most profound puzzles in physics. Solving it could unlock the path to a theory of everything, a unified understanding of space, time, gravity, and quantum mechanics. So, what are black holes, really? They are not just destructive objects. They are cosmic laboratories, places where the laws of nature are pushed to their limits. They show us that time is not absolute, that space can bend, that reality itself is deeper, stranger, and more interconnected than we ever imagined. They challenge our assumptions, they stretch our imagination, and they force us to confront the unknown. We used to think black holes were the end. Now we suspect they may be the beginning of something greater. In their silence, in their darkness, they speak of the universe's most profound secrets. We're listening, and slowly, we're beginning to understand. If you find this content valuable, don't forget to like the video, subscribe, and turn on notifications for more mind-expanding educational content. Thanks for watching, and we'll see you in the next video.